Okay, this is my project I decided to do today on a stepper motor driven by a PIC processor. And the PIC processor is a 12F1612, and it's a very simple project. As you can see, there's only really a stepper motor and a PIC processor and some batteries and two little resistors and a couple of these photo transistors. And they are just, I wrapped them with shrink tubing just to cut out the rest of the light, but they're maybe 50 cents a piece, and the processor is maybe about 75 cents a piece. And that motor I got off eBay for I think about $8 or $9. Very simple project, not a lot of stuff involved, and there's actually only 32 bytes of instruction. I am using assembler as my language, and the soldering station makes a good platform for a camera. And I'm also using a Windows 8 based PC, and just tap there for focus. And I'm using the current software I have right now, which is the MPLAB X IDE version 3.25. And I'm only, actually it's about a 500 megabyte download. So you got these little three I guess programs or icons with it, and I'm only going to use that one to do the whole project from start to finish. And I also got a spec sheet, or they're called data sheets actually, but it's a 400-page document on how this chip works. And it's the 12F1612, and that's it right there. I'll talk about that in a bit, but it's I always like to print it out just because it makes it a lot easier to jump back and forth between the book and the project. I'm using a PIC 3 programmer. They're like $48. I'm just giving prices just so you have an idea what is invested in making a little project like this. If you're a hobby electronics guy, then that's, or girl, that's great. So the way it works is I'm programming from the USB port into this PIC Kit 3, which will program this little chip right here. And I've wired it in with all these little purple wires. It's a little redneck, but it works. And I've also had to put a 5-volt power source onto this. I know it's really weird because don't USB ports have 5 volts anyhow? Whatever. Anyhow, it's roughly 5 volts. It might be 4.5 volts for all I know. And that is a blank chip I will be programming in this video. So we're going to try and go from concept to finished product in, I guess, about 25 minutes. So this book, yeah. There's some stuff in this book that I think is really useful because while we're programming this, you'll see a lot of stuff that is directly related. Oops, sorry, bumping camera. So let me just briefly talk about what's in this book. Things like this. This pinout is really important for these chips. And obviously that's positive 5 volts roughly. It could be anything from 3 to, I don't know, 7 or 8. And negative voltage right there. And these are all my I/O ports right here. I/O 0, 1, 2, 3, 4, 5. And what we're going to do is I'm going to drive the motor directly with I/O ports 4, 5, 0, and 1. And I'm going to use RA2 and RA3 for the photo interrupters that are being used right here for this. Actually, what can this thing do? So yeah, as I move these little photo interrupters around, the sensor on the photo interrupter senses that the little paddle has swept over the light that is coming from the ceiling. So I can move these as close as I want. Poor guy. The torture. Yeah, okay, so it's kind of mesmerizing, don't you think? Yeah, those, I think, did I mention it, that these things are like 50 cents a piece? Yeah, I did, didn't I? Okay, so what else is in this book that I think is relevant to this program? Okay, yeah, this program, or this chip anyhow, it does something called banking or paging to get between various special function registers. And what we will be doing is banking from one register to the other. It's just part of the way Microchip makes their chips work. So bank 0 is the main bank, and I will be going over to bank 1 probably first of all and programming the I/O port, and it's over here in bank 1 byte 8C. Anyhow, this register right here, 8C, it has all the information for controlling your, actually, let me just pull the chip and stop the whole project. There you go, nice and quiet. Okay, so where was I? Oh yeah, okay, so this bank 1 register 8C controls the I/O, or the input-output port, and you can put a 0 or a 1 in any of these little bits, and it will create either an input or an output port. Right there. It's kind of cool, eh? And over here on bank 0, you go to register C as well, and then you have the ability to either pull off or put into the register your data in order to work your I/O port. So that makes it kind of interesting to note how that works. What else? Okay, yeah. So okay, yeah. I'm using assembler as the language of choice with this, and there's really 49 instructions with this particular chip, and that's about 38 of them. The other 10 are right there, 12. And it's really simple language to learn. Probably take less than a day to pick it up, and it's a fantastic language. There's only like 15 pages or 10 pages to read to know how to program an assembler. This is just the general layout of all the instructions. More detailed explanation is right here, and you can do anything that you want. This just shows you the syntax. Some of the instructions will be used, like call. I'll use the call instruction. I'll be calling a label, and decrementing a file register, and probably clearing a file register as things happen. Bit clearing. I think I'll even do a bit test in there. Bit test a file register and skip to the next line if it's set. How cool is that? Oh, and decrementing file register and then skipping to the next line if it's a 0. And okay, just the syntax is fairly straightforward. Yeah, you just kind of read through it and get an idea how it works. You actually should read this before I start this program or this quickie tutorial, because you're going to find that I'll be talking about stuff you might have no idea on. But yeah, okay, there's the book. Okay, so the project. What am I building? Well, I've got a, I'll do a quick schematic. By the way, this is the code right here. There's only 32 bytes. This stuff up here is something that generates by, the computer would generate it. We'll see what it looks like. Okay, so the stepper motor has 4 wires, and they appear to be like 2 coils coming out of the stepper motor, and 2 coils that seem to have about 30 ohms across each, so it's easy to figure out which wires are which. Basically, you have 2 coils only. And I have a PIC processor, obviously, a PIC 12F1612, and it only has 8 little pins on it. And I'll just write them out like this. Pin 1 is always 5 volts positive. Pin 8 is the ground. So I'm going to direct wire this stepper motor straight into my poor little PIC processor. They're fairly robust, so it's not like I'm going to heat it up or anything. They actually stay nice and cool even when I'm doing this vicious sort of project. Yeah, because, okay, well, for starter, I'm way underdriving this this little stepper motor. It needs like 100 times or 50 times more power to actually do something really productive. This is just a demo or a tutorial, just so you have an idea how stepper motors work. So, you know, don't think that I'm creating the ultimate program that'll drive that to do anything you want. It just barely flings that little stick around. Okay, so I have two photo interrupters or photo transistors. There's one right there. And of course there's a little resistor, 5 volts, ground down there. Let's see, how do I do this? A little lightning bolt, right? The arrow. And that's about 30K. Roughly about 30K. Depends how much light's sneaking in here. Tap into the middle of that to get a signal. And another one right here. And another resistor. 5 volts again. 30K roughly. It could be anything from 20K to maybe 40. Depends how much light you've got hanging around your place. And that's going to go to the other pin there that I will use as an I/O port. So obviously these two are going to be input ports, and these 4 are output to drive the stepper motor. And as you can see over here, there's the pin out, and it makes, I just have to remember RA2 and RA3 are the input ports. Don't know if I explained this, but I'm going to be driving this chip or this stepper motor using one of these waveforms. Actually, I like half-step drive. I'm going to be using that. These are the various types of waveforms that you can send to that stepper motor to make it move. So for example, this is a very common sort of step where you just pulse, like there's obviously 4 wires, right? So you pulse one and then the other and then the other, and it will force the stepper motor to go, let's say, clockwise. And if you went the other way, if it went this way, it would go counterclockwise. This one right here, the full step drive, it lays the steps over each other and it makes a bit smoother drive. And I'm just using this one right here because I kind of think it's the smoothest drive that I can do with this particular chip. And if you noticed that there's actually only 8 different types of sequences or waveforms here. This is basically time going this way, the 4 lines right there. But let's say at this point you can see where the A line is high, right? B is low, C is low, and D is high. And you can see how it goes along the next bit of time later. A is still high, B is low, C is low, and D is low. And it keeps going like that along based on time. And you actually, there's only really 8 different waveforms here. And what I will be doing is building a lookup table to generate all 8 waveforms. And let's see here. What else have I not talked about that I should be mentioning here? I think that's about it. I'm just going to go straight over to the blurry TV set. Click. Okay. Now, I am going to use, like I say, MPLAB X IDE and create this project using version 3.25. So double click on that and see if it ever opens. Oh, it's opening up pretty quick. Wait for it. Wait for it. There it is. All right. So, I'm just going to get rid of all this stuff so we have a nice blank canvas with which to work on. I always open up new projects the same way. Is this sitting so I got everything in there? I guess it's pretty good. This is my camera phone, by the way. Okay, so new project, I click on this. I will actually just say exactly what I'm doing just in case the camera is really blurry. I'm Microchip embedded right there, standalone project, and I click next. I'm going to select a mid-range 8-bit MCU because that's what I have. It's a, what did I say, a PIC 12 something? A PIC 12 F1612 right there. And then I click next. and I'm not going to use a debug program, so I just click on next, and it's asking me which programmer. I'm using a PicKit3. I click next, and it's asking me what kind of assembler or programming language. I'm using assembler version 3.25, and it came with the download, the 500 megabyte download, which is cool. Project name, pick a number. I'm going to call this, why do I see that up there? Call this test 24, I guess, nice number. And down here, the encoding, I'm going to select it as UTF-8, and that just changes the assembler into hex or something like that. Finished. Great. Okay, so let me just get rid of some of my other projects here. This is really the project right here, right? And I'm only going to do one of these things. It's going to be a source file. Build everything into the source file, and it's a new file, of course. We're going to make it right now. And it's going to be an assembler, I think I mentioned, and it's going to be a .asm extension. Click next, and they want me to give it a name. I'm going to call it test 24. Don't really, that's fine. Don't really care. Okay, so what is this doing here? I'm just going to get rid of this junk down here from my previous program stuff. I don't know. There, now it's nice and gone. Okay, so I'm going to start programming this right here. So what I usually do is I tab across a little bit just so I have some space for label or labels going down there. But there's a few directives you have to give the compiler first, and one of them is not necessarily relevant, I don't think. I'll just type it out and then I'll explain it to you. What that is just telling the compiler which processor I'm using. So it says list P equals 12F1612, and that's my processor. And this one right here, directive, is telling the compiler exactly where I want the code to be dumped on the chip's memory bank or memory. So it's going to be going into location 00 and building from there. So actually, let me just give a little bit of space there. And okay, I'm going to start just the code here. And the first thing I'm going to do is I'm going to move a literal into the banking register, and I'm going over to bank 001. So bank 01, I'm going to program the I/O port. So I'll move a literal into W, and I think I've decided that OC is the right one to match up the thing. So, and then I move that file, move the give me a second here, I'm just reading something here. Move the W register okay, to file register OC. Okay, so what that is I've just OC is very exact, literal that I'm using, and I'm placing it into register OC by moving the working register into file register 0C. Hopefully you understood that. I'll explain a little bit better next time. So that programmed the I/O ports to be 4 outputs and 2 inputs. Yeah. Now I'm going to run over to a different bank. So move literal into banking. I'm going to go over to bank 3. There's just something I got to do there. Actually, no, I'm not going to do that. I'm just going to clear a file register. Which one was I going to clear? Okay, I'm going to clear register OC in bank 3, and what that simply does is changes all the I/O ports so they're now digital instead of analog. When they're shipped from the factory, all these chips were set up so that all the pins were going to be analog, and that's not something we want, right? Hopefully, right? I'll move literal into banking register again. So I'm just going to go to the 0 bank now, which is the one where I have most of my programs set up in, or running in, I should say. And at this point, I need a label. And you could pick any label you wanted. I'm just going to use something called start. And I always throw a lower slash on there just because it separates it from any other directives or instructions that might exist out there that I might not be aware of. So what I'm going to do here is I'm just going to paste the rest of the code in here, because this obviously is very tedious, but I just wanted you to have an idea how code was put in to these things. Look at that, I grabbed the wrong stuff. Okay, so I'm just going to pull that out of there. I'm going to run and get the rest of the code. I think it was in, I think I left the code in 23. Oh, that's nice. Okay, so this right here is just me grabbing code from somewhere else. You would never have to do this. So just pretend you're, go get a coffee or something for a second here. Copy that out and go back to this one and paste that in there. Okay, great. Okay, so that's just the pasted code. The rest of that muck I was just doing was just scrounging it. Hopefully you understand that. That's the program right there. That's it. In its entirety, almost. Almost. Okay, so what I will do is I will explain how this all kind of works briefly. Obviously the first batch right there that we just saw, that basically set the I/O ports up and cleared out some stuff. Is that right? Move little to W, move little to W, W to far C, move little to W, clear that. Yeah, it just set up the ports and stuff. This is where the code really starts to make sense. So what this is it is bit testing the I/O, the two input ports. Actually, this one is testing the input port 3 to see if that paddle that was on the stepper motor has passed over the photo transistor and interrupted the signal from the light that's above there. And if so, it'll bit set file register 250. And what that is I've just created a flag by doing that. So that flag tells me that the paddle has passed over that photo transistor, and with that knowledge I know I want the paddle to go the other way. So same basic instruction right here. I'm doing another test looking at number 2. The battery is low on my camera here. 1 second, I gotta plug my camera in or else the video will come to a fast end. Thank you. Sorry about that. It's such a hassle building these videos, so I don't want to stop it because of something like that. Okay, so yeah, so right here it's checking the other photo interrupter, and if it happens to be sensing the paddle interrupting, it will clear that exact same bit in register 25. And the reason for that is it just gives me an idea which way things are traveling, or the paddle is traveling, so I can create steps going in the right direction. And at this point right here, where my little cursor is, it's now addressing the issue of which way I want the paddle to move. So I've increased the register that keeps track of the position of the stepper motor. If the bit is cleared, and then I would decrement the same register if the bit was set, or actually it's backwards, isn't it? You know what I mean, because it did a jump right over that, right? Anyhow, that is creating a direction travel for the byte, or the stepper motor to move. Anyhow, there is register 20 keeps track of the location of the stepper motor. And at this point right here, I am going to try and isolate the last 3 bits of that byte by moving the number 7 into a literal and then ending it with that register. And with that, you get the last 3 bits of its position or its next position. And with that, I take that knowledge in the W register and I call a table, which is right down here. And that number that I had, that the last 3 bits of 20, I add that to register 02, which happens to be the program counter. So it's just going to add to the program counter and jump down to one of these bits of data right here. And this is my waveform for that half-step wave that I'm trying to create. And this data actually, when laid on the I/O ports, will simulate that. Anyhow, return literal in W, so it's going to grab that and put it in the working register and run back to whence it came, which was right here. And move the W, it'll move that data into file register 0C, which, if you remember from what I was telling you before, it's the output or the I/O port. And it'll lay it straight on the I/O port. And since the stepper motor is moving a little bit slower than, a lot slower than this chip, I have to create a delay while the step is moved by the stepper motor. So I move this 68 into register 21 and I just loop it on down. This is just a decrement loop. It just slows down the time. Well, I should say slows down time. It creates a delay. And then when that delay is created and done, we go back to the start and we do the whole thing again. So that's the whole program right there. Just looping around and moving that stepper motor left or right based on what it last saw in the way of which interrupter or photo interrupter was interrupted. Is that it? Yeah. Okay, so that program is ready to be put into a chip. And what I want to do is now I have to build something called a configuration bytes actually. So I go over to the run and set the configuration bits. Actually, what I need to do is just pull this little thing up. There is none. Okay, so I go over to run and I set the configuration bits. So this window pops up right here. Co-op await. There you go. And these bits, or these bytes here, this is to do with the way the chip will run. And it's kind of important. Without this being set up, the chip will not run. Things like exactly what kind of oscillator I want. For instance, I want an internal oscillator because I don't have room for an external crystal or anything like that. So that's why I have to set that up. This one right here, for instance, I have to change this so that instead of having a memory clear pin, it's going to be a digital pin because I need all my pins. I got 6 pins, the whole 6 I need. This right here, this chip has a brownout detection system, which means that if it senses the power fade at all, it will reset. And I don't want to do that. I'm going to disable that because there's so much EMF coming off of that stepper motor that it'll probably brown out constantly from the abuse that I'm giving this. What else? Pretty much this is all fine. This right here, we're actually doing a high voltage programming because we have 5 volts instead of 3. And this watchdog timer, I wasn't using it, so I'm going to disable it. And that's the way I like my configuration bits set up. So I'm going to generate some source code that I can see, and it's in the black right here. And I will cut and paste this and stick it into the front of my program. So copy and bring it up to here. Oh, let me just pull this window down. And I'll paste it right here. And now my program has that at the very, near the top anyhow. And my rest of my program is all down here. and that's essential just to set up the compiler to program the chip's main, I guess, features or whatever, eh? Anyhow, let's run this. So I'm going to compile this, and I use the little hammer right here to compile it. So I just click, well, tell you what, let me just pull this window up here because you can see the compiling happening right here when I click on this hammer. So I'll compile it right now, which means it turns it into code that the chip can use, and that's it right there. Down the bottom right here it says build was successful, so that's great. Now I want to take that compiled information and shove it into that chip, and that's what this little icon right here does. So I click on that, and it shoves it into a little chip through my USB port into my PIC 3, right? So it is done, verified, and complete. So I'm just gonna see, my camera is powered up. Maybe I'll just unpower it from here. Might have a little bit of life left in it. And I'll pull the chip and I'll stick it in the project and it'll be all done. Okay, so there's my chip that was just programmed. Run over here, stick it in, stick it in there. And the project works. And that's it. Thanks for watching, and sorry for the jiggly video, but we'll talk to you later.